Well, that's the time. Well, welcome everybody. So, I hope you have had some time to think about it. And of course, on one hand, we can always calculate how much time would it take to reach the maximum height. And then we can calculate how much time does it take to reach the ground. Yeah, that's what we call time up. That's what we call time down, right? And if we add them up all together, that will give us the total time. And normally that would be the best case scenario, because for most of the problems we would have to calculate time up anyway, because that's what we do normally if we need to answer the question about maximum height as well. However, in this particular situation, no, we don't really need any extra data if we want to calculate just the total time. We know the x and y components of initial velocity, and we know that the landing position is 20 meters below the launching point. So that's completely sufficient to calculate the total time if we need that. And from that point of view, the problem related to the projectile motion is no different at all from this problem about the free fall we have solved before. Because if it's just about a vertical part of the motion, we just need to look at, well, as we say, the motion of the shadow of the ball. Yeah? The shadow moves up and down exactly like an actual ball if that ball would have been tossed up with this initial velocity. This is just one component of the actual velocity of this projectile. And during the motion of the projectile, the position vector, some call it radius vector, changes. And the position vector always has two components. For example, this blue arrow represents the vertical component of the final position vector. And this blue arrow represents the horizontal component of the final position vector. And if we choose, as we always do, the origin at the lowest position of the ball, relative to that choice, well, y initial will be equal to this number, 20 meters. Y final will be equal to this number, 0 meters. V y initial is equal to 14.3. The acceleration points down. It has a component which is equal to negative about 10 meters per second squared. And if we write the motion equation, which includes the total time. Yeah. From here all the way up to here for the ball, or for the shadow of the ball, from here all the way up to here. And if we plug in the numbers, we get the quadratic equation, which we always can solve using quadratic formula. So this is a review question. We've done exactly the same math before for a motion which had happened just up and down, but exactly the same reasoning works and for the projectile. And of course, as I said, we can answer the same question differently. We could have calculated time up and time down, and if we know the time, we can calculate all important geometrical variables like the range, that the horizontal distance traveled, which is just the x component of velocity times total time, maximum height, which is equal to, well, the position when the time is equal to time up. So there's one more problem, the last problem I want to talk about related to projectile motion, and we move on to the next topic. We read and we decompose the text into the words which give us the most information. And the most information is hidden here in this word, highest. So right here, at the highest point, there is no vertical component or velocity, only horizontal component. Velocity is not zero. Well, velocity itself is not zero, but the vertical component of velocity is zero. And, well, what can we do? Y max, R, the range. So it was shot like here. What expression can we write? The first expression comes to mind is just for the range. The range equals the horizontal component of velocity times time, total. However, first of all, the vertical component of velocity always equals to the launch speed times cosine of the launch angle. That's what we call V0, V0, the launch speed, that's the launch angle. And the total time in this situation is equal to time up. Everything stops. Well, it blows up over there, so it disappears as a projectile. And that's it. All other relationships supposed to be related to the vertical motion. So what can we write? Well, for example, at the highest point, the velocity, at the vertical component of velocity equals 0. So and if we use the trigonometry, that should be the initial speed times the sine. Actually, I don't use 10 yet. I'm just going to use a variable which represents the g equals 10. So far, we have so many unknowns. We don't know this, we don't know this, we don't know this. Yeah. So we're going to keep writing. What else can we add? Well, we could have added the motion equation, y equals y initial, etc., etc. However, again, that equation includes the time, which we don't know. Yeah? So I suggest let's try using the third equation, which has no name, because it also includes initial velocity and distance, vertical distance traveled, but it has no time in it. So 0 squared should be equal to 0 initial squared, well, plus 2 times v initial squared plus 2 times a times delta y. That's how we write it in general. And now, the initial component of vertical velocity is this. We should square the whole thing. Don't forget these parentheses. People sometimes forget parentheses, and they square only the sign. And they don't square v0, the speed itself. Now, well, plus 2 times negative g times y max. That's what it is from here to here. That's the displacement. It equals to maximum height reached. Now let's see what we know. We know the range. We know this. And is it sufficient? I don't know, actually. Let's see. So first I want to rewrite the equations. The equation number, now I'm going to start using numbers. It's just easier to see what we can do. So the range equals 125 meters. That has to be equal to this times cosine of theta times time up. My first equation. My second equation. In my second equation, I just want to resolve it. So take this. So this equals to that, basically. The initial speed times sine of theta should be equal to g times time up. Why do I want to write these equations in this way? Because I want to get rid of time as a variable. And the easiest way is just divide two equations. This divided by that should be equal to this divided by that, and time cancels. So 125 over this will be equal to this times cosine of theta over g. Now it is time to use the third equation. So we can also resolve it. Just take this negative term and bring it over here where it's 0. So we're going to have speed squared, sine of the angle squared will be equal to 2 times g times height, 233. So that gives me a clue. You see, I have speed squared here, and here, if I multiply this, well, cross multiply, v squared, I get exactly the same term, v squared. So this equation I want to just cross multiply. What does it give me? V naught squared times sine of theta times cosine of theta supposed to be equal to g times 125. And now I can repeat my simplification action. Divide both sides. If I divide this and this disappears, it gets cancelled. So if I do that, what do I have left? So sine squared, sine. One sine getting cancelled, one sine remains on the top, right? So sine of theta over cosine of theta will be equal to 2 times 233 divided by 125. That's a relief. But finally, we get an equation which is solvable. Well, first of all, we should simplify this expression. Sine divided by cosine, what does it give us? That's exactly right. So 2 times 233 divided by 125. $3.7 roughly. So if we take the inverse sine of this, that should give us the launch angle, the inverse tangent, where is it? I don't see. The inverse tangent of 3.7, about 75 degrees, 74.8, 75. So after those algebraical manipulations, we get one more quantity known. Well, you wouldn't have to do it this way, but this is the shortest way. Basically, what we have here, 3 equations and in 3 unknowns. That's solvable. You just have to manipulate, solve for one variable, plug it into another, then another. But sometimes there are some mathematical tricks like canceling things out, which just save time. And now, of course, everything is done. If we know the launch angle, now we can use this angle to calculate the launch speed. If we know speed and angle, we can calculate the x component, the y component, time, everything. Done. Any questions? Okay. No emails, so no questions. Moving on. Now we start a new topic. We're going to start talking about forces. This is a very, very old science. So about, I would say about even 200 years ago, people who could have solved problems we're going to learn how to solve would get PhD in physics for that. Now, it's, you know, it's so simple and straightforward that middle school, high school student can do some of the problems we're going to do. What is a force? Well, of course, we have to start from a definition. And a force is, well, what it is here. A pull or a push. There are two kinds of forces. There are forces which we call contact forces. I have to hit it. I have to touch it to apply a force. That's the example of the contact force. But there are forces which do not require object to be touching. One of the forces is, what do we say? Gravity. Gravity pulls everything down without touching it. There is another example, very common, and you know it, force which doesn't require touching. That's electrostatic force. We're going to talk about it, well, maybe. Well, I'm going to talk about it when I will teach PY 106 course. I'm not sure about you, if you're going to be taking this course ever. But PY 106 course starts from static force, electrostatic force. So, we're going to talk about mechanical forces so far. Mechanical forces such as what does stop it? Friction. Force of friction. Now, I'm not falling through the floor. You're not falling through the chair. This brick doesn't fall through the tabletop, which means there's a force which prevents it from falling. We call it normal force. In physics, the word normal always has mathematical meaning. Normal, it doesn't mean it's good, you know, better than, no. It's always perpendicular. So in this example, for instance, a wooden brick on an incline. It doesn't slide. There's only one reason for that. Friction keeps it from sliding. But also, it doesn't fall through this wood. So now, there is also a force, which we call normal, which is perpendicular to this surface. Eventually, it would start sliding. So in that case, what is the reason for this block to slide? Well, gravity. Gravity starts strong enough. Of course, friction doesn't disappear, but that's not going to be the same friction anymore, different. We'll talk about it in great details later. Another very important force, force of tension. Yeah. In any string, cable, rope, we have a force of tension. Force which is acting on this ball from this string. Does my hand, does my hand touch this ball? No. So my hand is not the reason for any forces to be exerted on this ball. How many forces are acting on it now? Two. Gravity, because there is always gravity well, unless we are in outer space. And, well, if you see anything touching means a force. This rope is touching this ball, there is a force. We call it tension. There is another force very similar. We call it elastic force. You know. Any spring, well, if we apply a force to it getting stretched, like here, for example. So the force of gravity acting on this weight, on this mass, and because of that, this weight is acting on this spring right here. The spring stretches, well, not infinitely long, yeah. But elastic force basically is the reason for the force of tension. The only important thing about strings, we neglect any possible stretch in it. So we think that any string or cable or rope always keep its length. And the spring, of course, is not. Yeah, it stretches. That's the difference. Physical nature is the same. Well, this is a short list of forces we're going to talk about. I didn't mention a push. Well, we know what it is. This, yeah. When we apply a hand or a stick to something, and it makes it, well, it exerts some force on an object. That's a very important statement. There is only one exception, but I'll talk about later. Every force is a result of interaction between objects, well, two objects. The apple is interacting with the earth. Yeah, there's a reason for each force. So, and the earth pulls on the apple hits Newton. Newton invents gravity. Yeah. Well, explains gravity. But the apple, in turn, attracts the earth. Yeah. So this is the apple, this is the earth. Huge object attracting small object. And there is another small object attracting the huge object. So if I would ask you, yeah, Earth. I would ask you this question, what would you say? Earth. Well, at this point we don't even have to think, we just have to know. Again, Sir Isaac Newton, well, he left several important laws of nature in mechanics, in optics, in thermodynamics, in fluid dynamics. In particular, he left the law which has a name, Newton's third law. And Newton's third law tells us if you have two objects interacting, the force first object exerts on the second has the same magnitude but opposite direction relative to the force the second object exerts on the first. So if we have an apple, 100 gram, times g, so the force of gravity acting on the apple will be equal to 0.1 kilogram times roughly 10.1 Newton. Exactly same in magnitude force the apple exerts on the earth. Well, the difference is because the apple is so light, the earth makes it move very easily. But because the earth is so huge, the apple practically doesn't affect the motion of the earth. So that force which the apple exerts on the earth is nothing relative to force of gravity from the sun or from the moon. So the effect is different. Forces have the same magnitude, but the effect is different. So this is a picture of many, many possible situations when we should think about the Newton's third law. The swimmer lady, she pushes on the wall. So this is the force acting from the lady on the wall. The Newton's third law tells us that it's supposed to be a force which has opposite direction and same magnitude, which is acting from the lady, from the wall on the lady, and that force propels her. There are several other situations you've met before. Any kind of a collision, any kind of a push or pull. It doesn't matter if you have two objects of same mass or same size or very different. Here interaction is happening, here interaction is happening, here interaction is happening. In any situation, the amount of force, which is a word for the magnitude of the force, which one object exerts on another, equal to the amount of force or the magnitude which that object exerts back. The effect will be different, but the magnitude of the force is the same. If you have a ball falling down, well, an apple, force of gravity we've discussed. But when it hits, what's happening here? Well, the ball hits the bench. According to Newton's third law, the bench hits the ball with the same magnitude, and that's why it reverses its direction. Now, this is again a picture from the past. Let's imagine, what does our common sense tells us? Of course, if we had only one person pulling on the rope, in that case, again, you start moving it from rest. It starts moving in the same direction as the rope points. If another person starts acting by pulling, and the object starts the motion from rest, in that case, it's going to move like that. What is happening in real life if we're applying two forces simultaneously? We know that in this situation, neither direction is correct. In this situation, well, or in that situation, you have people on ice. The resulting effect is, well, something like this. So this red arrow should represent the force due to the strong man. This short arrow should represent the force due to the boy. A force is a vector. It has a direction. I can pull or I can push due north or east or up and down. So when we draw a vector which represents a force, we try to show the magnitude, well, respectively, strong force, long arrow, weak force, short arrow. But the most important fact now, that to figure out what should happen, we should add these forces as vectors. We should use tail to a head rule. And that blue arrow represents what we call the net force or total force acting on this object. So that's the first fact we can extract from many, many experiments with several forces. Not individual force, but the net force matters. And the second fact, again, we start moving from rest. It was not moving, and now it is. Change in the velocity means there is acceleration. So the reason for that acceleration is the net force. So if the net force is not zero, The object must have some acceleration. That's it. And now we need an expression, a mathematical expression, which relates the net force acting on an object and acceleration. This expression is a definition of net force. Net force, an abstract algebraical vector, which is the sum of all forces acting on an object. But on the other hand, this is another symbol for the net force, Greek capital sigma. On another hand, where is it? Here. On another hand, the net force is proportional to the acceleration, or acceleration is proportional to the net force. Well, the third element which is involved in this relationship is the mass. This is the physical nature of what net force is and what the mass is. The net force results in the acceleration, and the mass tries to decrease the effect of the net force. But of course, we don't like laws with fractions. We just multiply by m, and this is how we usually state the Newton's second law. The net force acting on an object is equal to the product of its mass and acceleration. Now, let's go back to a couple of slides. When we have to solve a problem related to forces, we must see all forces acting on the object of our interest. Like here, what should I add? Well, this is the force acting from a wall. Of course, in a real life situation, I would have to add force of gravity acting on this lady. There is a, well, buoyant force. You know, if you immerse in water, you feel lighter. There's a force which kind of moves you up the surface. And of course, in real life, there is some force of viscous resistance. We don't usually draw a picture like that. We usually draw something like this, an object, and then we draw forces. One force, second, third, fourth. And a picture like that, which only shows forces acting on the object, has a name. We call it a free body diagram, because this diagram doesn't show the actual object. It's up to you. I usually draw a little actual, picture of wherever it is, like a car. And now, what we have in this example, we have two forces directed to the right, one force directed to the left. If I want to ask a question about the net force, what do? I add them up together as vectors. That's what we have to remember. I choose positive x direction, and relative to that choice, two arrows have positive components, and one arrow has a negative component. So when I'm writing this expression, you see, a vector, a vector, a vector, a vector, I always have to write a plus. I am adding forces. But when I make a transition from forces to numbers, I have to take into account the direction. If this force has a negative component, well, I am adding negative component. That's what I'm doing here. And that's the net force. What does it tell me? It tells me that the net force has magnitude equal to 110 newtons, and it points to the right because it's positive. Now, we used to think about mass as, well, a parameter which describes how much stuff can we fit in something. Like this is an empty glass, but if I fit it with 1 kilogram weight, it's heavy. But on the other hand, now, due to Newton's second law, mass becomes a measure of inertia. Inertia, in general, is a property of a system to keep its current state. So, for example, if something is moving with constant velocity, it will be moving with constant velocity unless net force starts acting on it. So we don't need a reason to keep it moving with constant velocity. And that's the first Newton's law. And if we have a heavy object and we have a light object, and if we apply the same force, the result will be different. For a light object, the acceleration will be large, and for the heavy object, if we apply the same force, the acceleration will be small, low. Well, am I touching the glass? No. So what is the reason for this glass to be in the motion? Well, physical reason is this piece of paper is acting on it. And the name of that force is what? Friction. Yes, exactly. There is a force of friction right here acting from this piece of paper on this glass. My hand is acting on a piece of paper, but my hand is not acting on this piece of glass. And, well, if I slowly move it, you see, it follows the direction, the motion of the page. What's going to happen if I move it very quickly? Well, in that case, because it has a relatively large inertia, when I do it very quickly, the inertia keeps it from moving. The time of action on this is not enough to actually make a significant change in its state. So the inertia, sometimes it's a good thing, sometimes it's not a good thing. Every time if you are riding a bus and the bus suddenly stops, what do you feel? That's the inertia because, well, the nature, tries to keep your current state, which was traveling with constant velocity. Now, in general, we have only two separated cases. Number one. Number two. Number one. Two conditions should be fulfilled. The net force acting on an object is zero, and the object is at rest. In that case, we call it equilibrium. Like right now, we all are in equilibrium. We experience forces, gravity, normal, but the total force, the net force is zero because those two forces cancel each other out, and we're not moving. Velocity is zero, we are at rest, equilibrium. So for the equilibrium, in general, if we have a complicated situation with many forces acting, the sum of all x components has to be equal to zero. The sum of all y components has to be equal to zero, which automatically means some of these components could be positive, some could be negative, otherwise it wouldn't be possible to make it zero, or they all have to be zero. And another case is just a general case when net force is not zero, which means there's acceleration, object speeding up or slowing down, like in this situation. And this is a common point of confusion. So we draw many arrows, but when we want to apply the Newton's second law, we have to draw and we have to use those forces, those arrows, which represent forces acting on my object, on the object of my interest only. So this is the force acting from the object. That's it. The answer is no. We cannot include the force exerted by an object into a free body diagram related to that object. If I wanted to, I could have drawn a free body diagram for the wall, and in that case, I would have included this, would have included that force. But the free body diagram for the lady should not include the force exerted by the lady. It should include only forces felt, by the lady. And we already had that free body diagram before. So here the answer is no. Let's do some exercises. This is the situation we're going to talk about right now, the equilibrium. What is an equilibrium? What object? All of them. This mass is in equilibrium. This scale, everything. So we have to choose free body diagram for which object do we want to use. Well, here we have three forces, 1, 2, 3, acting on this little nut in the middle. So we should draw the free body diagram for this nut. This is actually 500 gram weight. So 0.5 of a kilogram times 10, 5 newtons. There is a force of gravity acting on it, and it equals 5 newtons. But it is in equilibrium. What does it tell us about the force of tension acting on it? It also 5 newtons. So gravity 5 newtons down, tension 5 newtons up. They cancel each other out. This is for this weight. But that's not the system of our interest. The tension here is 5 newtons everywhere. So the same 5 newtons now acting here down. 5 newtons here, but what do we read? Does it look like 5? What do we read here? Does it look like 5? Why? Because of those angles. I could have just have one scale attached to it, and in that case we read 5. But if we start changing, that's the third force now in the place, and the third force changes, and it depends on the angles. For example, I can move it like that, and numbers change. For every situation like this, we always can draw a free body diagram, and we can apply the condition for the equilibrium. That's what I'm going to do for this picture. From a physical point of view, that's exactly the same situation. So you see, the net force must be equal to 0. All right. First of all, I don't really need the actual lady in my free body diagram. There is a point, well, this point, like my nut over there, which is being acted by 3 forces. You can see only 2. Yeah? Which force is missing? Gravity. So there is, of course, the force of gravity, mg. And now we'll have to draw 3 forces. That's supposed to be force number 1. That's supposed to be force number 2. We call it F, legs. We call it tension. That's supposed to be the force number 3. We call it gravity. However, this is not a good picture yet. What's wrong with this? The sum of all forces must be equal to 0, which means if we add these arrows according to the tail to a head rule, we should get 0, which means let's say we start from mg, then we go this way, and then we go that way. That's not 0. This picture shows a certain resultant, so this picture is wrong. The only reason for that is my picture not drawn to scale. That's it. So I just have to redraw. I have to fiddle with length of each arrow to make a triangle. So I want to try again. Okay. Actually, I think I have. Yeah, I want to try again. So this is supposed to be a force of gravity acting on the lady. Now, the force from the feet should be directed at 15 degrees to the horizontal direction. And my force originally was too long. Probably I should stop somewhere here, because my third force, the force of tension, should point right at the beginning of the force of gravity. In that case, the resultant is 0. If we start here, 3 forces, and we end here, that means there is no resultant. It is 0. That's it. Physics is done. The rest is what? Math. It's about triangles. So what do we know? Well, we know some angles. For example, this is a 15 degrees angle. What else do we know? This angle between the vertical direction and the force of tension is supposed to be 31 degrees. That total angle has to be 90, because that's the vertical direction, that's the horizontal direction. 90 minus 15, this angle is 75. See? This is not a right angle triangle. So we have two options. The option number one, we make right-hand triangles, like this, for example. We can draw a perpendicular. Actually, we can call this x-axis, we can call this y-axis. And now we have a very clear situation. Each force has components, and the sum of all components must be equal to 0. So that's an exercise for the lab, probably tomorrow, I hope. Or another way, you see, this is a right-hand triangle, and this is a right angle triangle. You know all the angles, and you know that this plus this should be equal to force of gravity, and force of gravity is 55 times 10, 550 newtons. So if you know one side, you can find all the angles. You need to know the angles. You can do the geometry, and you can find all other sides. And last option is, well, remember I had a slide. You can use a cosine theorem, or you can use sine theorem, depending on your choice. If you want to, for example, you can write that tension, magnitude of the tension divided by sine of 75 degrees, supposed to be equal to the magnitude of the force, the legs, divided by sine of 31 degrees. That's a sine theorem. So it is up to you. How do you approach this math? There is no physics left. We need to know the sum of all forces equals to 0, and if we add 3 vectors, the resultant is 0. It must be a triangle. Now let's talk about second possibility. We have two objects here. There is force of gravity acting down on this. There is a normal force. But these two forces cancel each other out. In general, we should think of possible force of friction between the tabletop and this wooden brick. And of course, there is a force of tension due to this string. So, for the object number one, the equation, the Newton's second law, should be written like this. The mass number one times acceleration number one should be equal to force of tension minus possible force of friction. Normally, we neglect friction. In that case, the problem even simpler. Well, if there is no friction, if nothing is holding on the object number one, what's going to be happening? This is going to be moving down, that's going to be sliding to the right. So, we can write the second Newton's law. 20 more seconds. Second Newton's law. So m2 times g, that force of gravity acting on the second object. And that's going to be the force of tension. Well, these are different forces. That force points to the right. This force points up. However, that's a string which can't be stretched, and normally we neglect its mass. So it's easy to prove that this magnitude will be equal to that magnitude. So m2 times a2 will be equal to gravity, well, minus the magnitude of the tension force. Well, let's call it magnitude. So you see, if we have a system means normally more than one object involved. One object is also a system, but we don't call it. We have to write the Newton's law for each object. Two objects, two laws. And final word is, if the string doesn't stretch, both objects travel same distance in same time. They have the same velocity and the same magnitude of the acceleration. And now physics is done. Starting from this, after having written all the equations, just algebra, just some math. All right, we'll pick from this up next time, but you're ready for the lab. Thank you. Yes, we're done, so everybody free to go.
What is that last character?
Or an A. That's my A. That's the magnitude. What happened? I just erased it. That's the magnitude of both accelerations. Again, remember, the acceleration is a vector. That acceleration points to the right. This acceleration points down. We can't say they have the same acceleration, but we can say they have the same magnitudes of acceleration. All right. Thank you. So I'm going to post the notes online and the link to the video probably in 30, 40 minutes. Yes?
Can we use the tension minus m times g here, the second equation?
Yes, you can. And what I didn't mention, because I was rushing, that in my mind, in this particular situation, I pointed positive y direction down. Yeah, so you see, that's why this represents a positive component of the acceleration relative to this axis. Thank you. So gravity also is positive relative to this choice, but the force of tension is negative. But you're absolutely right in your question. Let's say we had it chosen upward. In that case, I should have written this. But if you multiply the whole expression by -1, that becomes this. That's a completely equivalent expressions. So it doesn't matter how we choose the direction. We just have to keep in mind what is it.
Yeah. Thank you.
Sure.
The one with the woman against the wall.
Yes.
The force of legs. We're focusing on the woman. Wouldn't it be the force of the wall?
But that's exactly what I said. If we're focusing on the woman represents the system of our interest. We cannot include force acting by the woman.
Yeah, in the one, she's hanging onto a rope, not the swimming one. Yeah, that one there. it be the force of the wall on her? The force of her legs? The woman was of interest?
Well, I suppose it's a matter of what the person who wrote this, calls it. I suppose we could have called it the force from the wall on the legs. That's not the force which her legs exerting on the wall.
It is the force of
This is the force exerted by the wall on her legs. That's why it's called probably F legs. I don't know. So this is just a shortcut, but the full name is the force acting from this wall on her legs. Yes. That's why it's supposed to be a part of the free body diagram for this woman.
Thank you.
Sure. Thank you. And done.